Hi, Michael. How are you doing?
I'm very well, Ashish. It is good to see you again.
Yeah, likewise. So thank you again for agreeing to meet with me and do this session.
Well, I think we're going to have fun. It's a conversation you and I have been having for quite a while, and some important topics. It's things that we learn about over the years by doing, and it's an observational thing that you and I both want to pass some of these things on to other people. They're hard lessons and important ones.
Absolutely. So I'll begin with the first question, Michael. Would you please share your background, including your time working at extremely large databases at Yahoo, eBay, and Teradata?
So I started out in the industry on a contract for EDS, and I went to work on geographic information systems because I have a background in my education about cartography and computing. And so it was this kind of interesting thing. But what's of interest about that is the scale of complexity of GIS systems. It's not that the data is all that big. This is in the 80s. Data size was, I don't know, 30 or 40 gigabytes. But we're talking about relationships that number in the, 10 to the 12th, right? Number of information nodes and whatnot in kind of a graph. But I moved on in my career to relational theory and started working at a little company when it was a startup called Teradata. It's not a little company anymore. This is my now second stint. In the interim of that first and second stint, I went on to work as a consultant, and mostly on Fortune 50 company systems, AT&T, Verizon, a bunch of three-letter acronym governments, all in really, really big platforming systems, telcos and whatnot. There are some significant ones where I went to work as a customer, right? And typically in chief architecture roles or similar CTOs, where you're building an ecosystem of things. One of them was at eBay. This is probably the largest and most significant thing, where I built not only some of the world's largest EDWs at 15 to 20 petabytes in size, and ended up being 20,000 to 50,000 production entities, which is a giant number. But also, you've got 50 to 100 major subject areas in those 50,000 tables and 500 concurrent and separate applications. I also worked at Yahoo, where as a chief architect for user data, another gigantic data problem, not just in how many users were using the Yahoo platform then, which is about 1 billion, but what do you do with all that personalized information, and how do you collect it? This is actually the biggest problem that Yahoo had. I also worked in a couple of other really large systems. We tried to save Sears. That didn't work out so well, as the market has told us. But we did do a good job cleaning up their analytics and giving them at least a foundation. It takes a lot of things to make a business go. I'm now back at Teradata. I'm an engineering fellow. I came back here to run the Aster Data Systems division, which I did for a while. We figured out what we were going to do with that tech. And now I'm doing strategic things and helping out my friends like Ashish and talking about technology problems.
It's fun.
Any commentary, Ashish, that you want to cover before we move on?
The discussion about Sears just reminds me of those good old days.
Yeah, it does. It was an interesting time. We listened. We did a lot of good work for that company. There's a very interesting concept that I've been promulgating about teams in companies of this size, not just within your small team. Most of us in our tech careers will have the opportunity to work in a number of teams. And sometimes, like I've had 3 separate teams in my career in which the individuals in the team were incredibly talented. And I was really fortunate to work in them. But it leads to this principle, which is essentially that the sum of a team is greater than the sum of the team's individuals. It's a very important concept. And so when you're working in a team, right, you have to think about what your contribution is to the other members of your team, and how the team can deliver things as a group that you can't deliver as individuals. If you're not working together as a team, challenging each other, helping each other solve problems, meet deadlines, giving up some of your own strategic wants and things to get theirs done, if you're not functioning as a team, you will not perform as well as other teams who are. And the more talented your team is not really a definition of how effective a team is, right? It's not the talent of the individuals, it's how the talent of the individuals is applied together. Okay? So the sum of a team is greater than the sum of a team's individuals. It's an incredibly important concept as you roll forward in your career. And those of us that end up being leaders, right? The question is, how do we foster that? Right? How do we help make those decisions for the team, and how do we mentor each other in areas where we're not necessarily as good as some other people, right? At the bottom of this, asking for help is one of the most important concepts that you can learn, right? So at any rate, don't forget that one. It's kind of a background about how personalization is important to building solutions, right? We're not going to be the only ones that use them or maintain them. So it's the sum of a team.
I think that's a really important and the words of wisdom that anybody who is getting into the workforce can really benefit from. Thank you for sharing that, Michael. You know, speaking of that, I think one of the things that you often talk about is we talk about data and the scale of data. You talk about the 4, 5 problems. Can you share more about that with us, please?
So earlier I mentioned in my background that, you know, I've always worked on big systems, and I just have a predilection to enjoy seeing big things actually get done. There's 2 principles here, but let's talk about, you know, how do you deal with, it's just a practical reality, but it will challenge you to think about scale. When you look at a number that is 15 digits long to 18 digits long, right? And we're talking about petabyte scale numbers. You can't visually look at that number and recognize its scale. And there's a huge difference in the 3 orders of magnitude between 10 to the 15th and 10 to the 18th, right? And the problems that you solve at 10 to the 18th are vastly different in implementation from 10 to the 15th. You guys are all saying, what is this? What? Write out a number, make it a random string of digits, put commas in it, and give yourself a 1/10 of a second to look at it and understand what the scale is. And you can't. You can't. And if you can, you're probably in the wrong business. So what we did, we learned this. We didn't even know that we were doing this. We were looking at storage amounts, and we're summing up the storage amounts in this data store that we created as a research project. And we're finding that there are 38 petabytes of spinning disk. It's a lot of disk drives. You guys can go do the math about what the disk drives were in 2009 to make up a 38 petabyte spinning disk problem. One is we couldn't figure it out. And so we didn't even realize we were doing it. We started counting commas, right? Is it a 4 comma problem or is it a 5 comma problem? And that's how we would start out the scale discussion of anything that we had to deal with. Loading data to a system is a 4 comma or 5 comma problem. One is because you have a 4 comma problem inserting data into a 5 comma problem. And now, without actually knowing what the number is, I know what the scale of my problem is. And as an architect who's designing things and having to explain things to other people, that's incredibly important. It tells me what the design constraints I have to deal with are. In a 5 comma problem, if it's not 1,000 units of parallelism, I'm probably not going to be successful, right? In a 4 comma problem, I might get away with an SMP, but likely it's 10 nodes, something like that, right? You can instantly look at a 4 comma or 5 comma problem and know where you are, right? And so this helps you in shorthand, but it's an example of how scale changes everything. And so when you're dealing with scale, and here's another example I just gave, right? Is it an SMP problem or is it an MPP problem? Like, these are design constraints, and you make that design decision up front. You've never even seen the data, but you've already made the decision, is this going to be on one node or many? because dealing with an MPP system is vastly more complicated. Just moving data to it is complicated because now you got to know network. Now you got to, all sorts of crazy things come up when you get to that 4 to 5 to 6 comma problem. And I've seen a 6 comma problem. It's not very much fun. It's pretty glorifying, but it's not very much fun, right? And this goes back to the teaming thing that I said earlier, which I'm going to reinforce, right? Some of your team members will be outside your circle of the team, right? At that scale of problem, it's all about optimizations. And the only thing that you can do is thread the needle through a whole bunch of optimizations to solve a problem. Generalization goes away the further up the scale you get. As that number gets bigger, right? The number of objects, the amount of complexity, the number of solutions gets smaller and smaller and smaller, right? So at the edge of scale, the only people who can help you are other people who have worked at that scale, right? So it's another concept of you really can't get away with doing anything but working as a team. The bigger the scale, the more important the teaming is, the more important skill is, right? And knowledge and asking for help. Ashish, did I cover your question appropriately?
You did, thank you. You know, one of the things that, you know, in data systems, the problem with scale is access paths, right? And everything is optimization problem at scale. What are your views about that? Could you share your experiences and views on this?
Well, I just touched on this. One of the problems that we face with optimizations is that they constrain the generalization of any given problem, right? You're going to introduce some complexity to make something perform in a particular SLA or way, right? You need something out of it. And at scale, the problem becomes that so many things are needed to perform in a particular way that you're left with a system that is only made out of optimizations. Optimizations may be cool. I'll give you an example. I can write the most obtuse piece of C code that nobody will understand, and it runs absolutely fabulously. It, you know, hits the registers right, it optimizes the cache line, it looks kind of like assembler, and it whistles and screams when you run it. But I'm not going to maintain that code. You're not going to maintain the code that you write, right? That's an optimization. If somebody else can't understand it, then you've optimized out its usefulness in a generalized way. This goes back to another thing that we'll probably talk about a little later, which is simplicity. But the point about optimizations is at scale, everything is an optimization. At those really extreme scales, everything you touch is an optimization. Examples. I built a system once and the vendor's backup product couldn't back up the data store. And, you know, they tried for about a year to solve a problem and it just didn't work. So I built my own. And this involved, you know, I've got a database, an MPP database. It's like 64 nodes or something, which for 2005 is a lot of compute power. I know we don't think about it that way today, but what I ended up having to do to build for that problem was create what's referred to as a nearline computing grid. So we took another set of nodes, a symmetric set. So we built 32 nodes, and then we direct connected with gigabit Ethernet, 4 links on one side to 2 on each node. We cross-connected them all. Then we wrote a bunch of software, I shouldn't say a bunch, it's about 10,000 lines of code, which does what we now think of as orchestration to set up a barrier method to pull data off of the machine as a unit, right? And so this is a fairly complex piece of software, but it's a use case that complexity, right, is oftentimes what you have to solve for. Now that system required us to know everything about networking speeds, buffer sizes, latency, right? We're talking microseconds even back then. So all of these things thread into a solution. There's also things about understanding at that time and at that scale, the impacts of networking on time slice theory. These are all Linux-based systems. Then it was Sun OS. And time slice management. We had to write a background test that managed the Renice facility. Well, essentially, we're managing the priority stacks in real time at runtime. These are wickedly complex problems. And if it wasn't for the fact that we were doing something at a 4, to 5, scale, we wouldn't have had to do that. And we would have used an off-the-shelf solution instead of spending 2 years of my time and 2 research programmers to go write all this foundational software and systems. So this leads to another concept, which we may or may not talk about later, which has to do with, how do you generalize things? But that's kind of a different concept. When do you generalize and when do you use an optimization is a product management and strategic kind of discussion. Ashish, do you have any comments about that? I know that you watched us do some of these things a couple of times.
And I'm glad you talked about simplicity because I wanted to go deeper into that, Michael. You're a huge advocate of simplicity in designing your data architectures and solutions. And we talked about how complex systems just makes it difficult because when you're operating at scale, that simplicity helps you optimize because it's really an optimization issue. Could you give us more business use cases like these and some of from your experiences where we can look into how simplicity is such an important principle and why you're a huge advocate of that?
Well, so I learned about this particular problem about simplicity in general while I was working on these very systems. And we built a system called Singularity. And the Singularity system was a profiling system that we used at eBay to do some pattern investigation, which I'll leave it at this, right? I talk about 5, problem, and this is a pattern which is made up of probably 10 to 20 tuples in a problem which has 20 trillion rows. Right? That's the pattern that we were looking for. And I don't really want to talk about why we were looking for that pattern, but it did have about a 25% impact on the stock price at eBay. That's how big a deal it was. Now, you look at the disparity of that, and that is a needle in a haystack. It's beyond a needle in a haystack. The numerology on that is I'm looking for a planet in an entire galaxy, right? And so that is the scale of the problem that we're looking for. Now, what I talked about I chose to build our own backup system. It was not my first choice, right? I spent 2 years doing it. We spent an incredible amount of thinking power and whatnot. If I could have used something off the shelf, it's something I could have done in a month, right? And I would have. Somebody else is responsible for it. I don't have to maintain it. I get the advantage of other people using it, of having something that's better tested. We had to test all of our own stuff. And this comes back to infrastructure, right? And the cost of building infrastructure to support something. Going back to my point about simplicity, in code, I can write a piece of C code, right? Some of you guys have probably been in interviews and other things. Write the smallest set of operators and functions in C code that accomplishes a task. In the world of writing software for commercial use, that is the wrong thing to do because I'm not going to maintain that code. You're going to maintain it first, or somebody else, or one of your brethren. You're going to walk into this thing 10 years after I wrote it, and the docs might not be available. And it might have been 2 o'clock in the morning when I write that ugly piece of code, and there's no comments in the code. If I can't understand that code, I have violated the principle of simplicity. All right, great. So you want to keep it simple and you want to keep it simple to understand. I'm going to give you another example, which is practical. I'm not really going to talk about business use cases. This is another thing that happened about the same time when I was trying to sell the idea for the research, which became the Singularity system. And so I mocked up the storyline about why we needed to go acquire all this data, right? 100 petabytes of data for 6 months is big. It's a big investment, $25 million at the time. Now, for $25 million, I have to go convince a lot of people to fund a lot of stuff, which has no guarantee of an outcome. right? It was a straight risk assessment. I can fix something for you, but it's going to cost this much, and there's no guarantee that I'll fix it. Okay. And this particular storyline was about having an elevator pitch. If I cannot explain that problem to my executive in the attention span of said executive, I'm not going to get my funding, right? And so this is also about conceptualizing what is it that you're trying to accomplish and staying on task and on focus with that. If you can't explain it, right? If it's not simple enough to understand with enough differential of intent versus cost, risk versus payoff, if you can't explain those things in 2 to 10 sentences in the elevator ride from the 1st to the 5th floor, you're not going to get funded because it's not simple enough. The issue isn't stark. And so explaining the complexity of the problem that I have in a 5 comma issue, executive doesn't care, cares about what's the benefit, right? So if you can't explain it, it's not simple enough. And by the way, one of my heroes in life is Feynman. And it's not because Feynman wasn't, well, he had his, there are things to not like about Feynman, but his great gift was to be able to explain incredibly complex things in simple ways that second year BS students could understand, right? Not in your 201 class, but in your 101 class. And that's why Feynman is one of my heroes. He exemplified why simplicity is the first rule of building anything. Keep it simple. The only time you want to deal with complexity and scale is when you have to. And sometimes you have to. Start with simplicity. I hope that explains. It isn't in business use case, Ashish, but the 2 storylines are absolutely true and were fundamental in my career change. Right? Everything I've done since, you start with the simple and then you fix the complicated things.
So I'm curious to ask, $25 million funding for the project. And what was your elevator pitch in those 20 seconds?
It goes to the use case that I was trying to solve for. We had a public relations problem with a particular hacker. And I said that I could build them a system that would allow data scientists to find that pattern problem. And I did, and they did. And it was worth 25% of the stock value.
That's a really fantastic story, Michael. Thank you for sharing, because what data can solve is amazing. And the investment required, the time and the commitment requirement is there. But the principle of having the simplicity is also something that, coming from you, who build that system, is very important lesson for everyone to learn.
So there's another principle along that simplicity line, which I'm going to deviate to and talk about. Please. One is that in almost all systems, you want the system to have 2 purposes, at least. If you're building a system for one purpose, why? That's already been done, right? And so how do we generalize something? So I was actually solving for 2 problems. One was the original research funding I got for that thing came from the security group. The CTO of the security group at that particular company said, "You're doing what?" Which comes back to the first thing that I was doing. We had built an EDW. They cost a lot of money, about middle 9 figures, a lot of money to buy one of those systems every 2 years. And so I was trying to find a way to do this much cheaper and at much larger scale. And so the hypothesis that I was testing is, I can build a system that performs at 10 times the power at 1/10 of the cost. So again, that's 2 orders of magnitude difference, 100x in the opposite direction. That was my original premise. And I had a technical premise. And when I was talking to the chief of security about that, he scratched his head. He said, "So you mean you could put X amount of data and find the needle?" Yes. Yes, I could. And that's how they gave me the money. And so that elevator pitch was literally on the walk from one building to the next building for us to go have lunch. And I remember this story because the VP that we both reported to separately walks by going in the other direction. He said, "Oh my God, the brain power. You guys better do something good today." And we did. Anyway, so I'm sorry for the sideline there, but it's a fun story about how we got to that. But a system should serve two purposes, or at least a hypothesis, right? Because we're not trying to solve for first order problems. We're always trying to solve for second order, third order problems. It's the same way with metrics. A simple sum doesn't tell you much. A simple sum over a timeline can tell you a lot more, right? And this is why we do advanced math, which I didn't get to take, by the way. I'll go terrorize my professors later. How do you draw a curve which explains, the geometry of a particular data set, right? Okay, fun. That's fun stuff that we can do later.
So thanks for the story. And talking about stories, Michael, let's talk about another story about data pipelines while you were working as a chief architect at Yahoo.
So there's a couple of prefaces to this, and one of the things I want to make sure that we talk about before we go is data as a prime. And I know it's not on our list, but we should probably talk about that too. There's a particular story at Yahoo, very different company from the places that I'd come from. I generally worked in very execution-focused organizations. eBay was one, many of the other places. Yahoo was a very interesting place because it was founded in the building of things, testing of things, writing new things. It was about innovation and applying innovation. Very interesting culture. Now, there's good parts to that and bad parts to that. So let's start with the principle that development in a large organization is a business process, right? We get in trouble with tech debt because it's a business process problem that us technologists tend to overlook. We don't think about, in the same way that I said that you guys will maintain code that somebody else wrote, and eventually you will write code that someone else maintains. That's a business problem. It's not just a technology problem, it's a process and business problem. So here we'll get to the story. So I'm responsible for all of the user data that gets generated. I'm the technologist that defines what are the platforms we're going to use, how do we acquire it, how do we store it, how do we build the BI tooling that we use to give back to the business, right? Because they want to ask business questions. They don't want to think about how to acquire a data set. And then, anyway, the source of all of that data is the ad pipelines, right? So all those ad impressions, and you're talking about tens of billions per day, right? This is another 5 comma problem. Story of my life, 5 comma problems. Now, this is a fairly complex task because the data is so big, you can't move it around. Yahoo at the time had 27 data centers around the world. And so you have to summarize this data. You have to roll it up into a second order metric. Now the roll up, there's a 1-minute file roll up, which is rolled up so we aggregate everything on a certain set of metrics to 1-minute files, and you write this into a directory tree, and then you propagate that not very far because it's too big. The most common set was a 25 terabyte per day after wild compression data set, which was the 10-minute impression files. And these things we would distribute to centralized locations and store them. Now, this is where the business problem part comes in. And it is the business process part is, when do you generalize a particular problem? When do you rewrite that optimization into something else? We've talked about optimization previously. And so as the CTO or chief architect for data pipelines and user data, I would go talk to the teams that were responsible for this. And the way that this was organized at Yahoo was very open society. And so they pipelined everything. All of the data was available on a pipeline. And so that 25 terabytes a day, you could touch that pipeline and draw that in. And the only thing that you had to do that was to go to the funding committee to say, I need enough hardware to do 6 months worth of this to solve this particular problem or generate these 3 metrics. Well, so there's 1,000 metrics, base metrics in that in that feed, 25 terabytes a day, okay, 1,000 metrics. So every week I would go talk to a new team and I would find yet another 6 to 12 months of that data pipeline stored in their own private place. Now, by the time I found the 50th copy, I was long past upset with my teams and my technologists because we had spent $1 billion of the company's money to store a bunch of data that was replicated, right? And oftentimes we did it in the same data center because we did not implement the business process of generalization. We didn't optimize the business process, which is the inverse of the technology problem, right? This is a business process problem, and in general, it's about architectural governance. Right? So we need to be really careful, particularly with data, about how we deal with the governance of data. Now, I mentioned earlier, I'm going to mention it again so that you'll probably hear it for a third time later on. Data is a prime. Software does not beget data. It used to be true because all data was private to a particular application. Financial applications used to own the ledger. Well, that's not true anymore, right? Because the moment that you export that data to another system, now you have to coordinate. In order to do that, you have to have standards and you have to have governance. At the very least, you write a contract between these two systems. And now you have governance and you have business process and you have to, how do you deal with bugs? How do you communicate, right? And so everything becomes a governance problem. These are business process problems. And so as technologists, we have to be just as aware about how we use the technology and where and when as we do in building it, right? The constraints that you're going to find when you build software for the enterprise or in complex systems is not the particular function you're writing, but what the effect of the behavior of that function is. Right. So anyway, that's the story of data pipelines at Yahoo. I loved my time there. Fantastic innovation in people. But my time as a chief architect, oh, I was an angry man. Angry man. That's not the only one of those stories. There's a bunch of them. I have another equal story about seeing the same join implemented 50 different times in Hadoop. That's a code quality problem. And that was even right? What do you do with a simple thing which relationally we've defined, and now you have 50 implementations, all of which behave differently? Talk about tech debt.
Yeah.
So complexity also happens when we don't pay attention to the business process and when we need to generalize something, right? And this is why sometimes the first time we write something is we're just learning about it. It'll never go into production. And then you write it for real, right? That happens a lot. This is why we do proofs. Ashish?
So yeah, that's really good because this is a good segue for me to ask you about your views on data privacy. We talked about data governance. Is there a correlation that you see between data privacy and governance? How does it impact the data pipeline architecture?
So one is data governance is a process for managing the structure of some technology. And in particular for data, which is its own thing, right? I mentioned this earlier, but data now derives software, right? Software is derived from data. Any AI, any virtual reality, even gaming, right? The data drives the application, okay? Now, in terms of privacy, privacy is a values thing. It is a very high level on macro values proposition. Now, as all of our countries are going through some attempts to define privacy, right? The EU has their set, which I'm grateful for. My own personal experience with this was that I helped build a bunch of the infrastructure and systems at Teradata in the 90s, which are all of your loyalty problems, all of your predictive analysis about what are you going to do about things like where do you put placement in the store, how you're going to pay, all of those kinds of things, which we took the data from you and we used that data to predict what you were going to do so that we could upsell you. All of those systems, right? All of the ad placement that you see on the internet, we built in the 90s. And we built all of those things using data about you to predict how we could modify your behavior in a particular way. Now, I didn't realize that I was doing that at the time. I mean, it's only in hindsight after building them for 20 years that you look at what these systems do and how they violate our, our privacy. Right? You can go out and find pictures of yourself on the internet that you don't have a right to, and you might be embarrassed by those pictures. So tell me how it is that someone else can monetize something about my personal life without my permission. And that is a fact of life in the internet. So this is a values proposition that all of our countries are going to struggle with for a while in the future. But I think you need to look at the ways that data gets used and propagated when you design systems, right? And sometimes, we have to be frank about this, right? It's not as stark as the scientists at Los Alamos building the first nuclear bombs. They didn't want to do it. They did it. And they had a big fight about it for a long time. It's not the same thing, but it's the same value system. And so you really need to look at that. My ideas on privacy are that, look, it doesn't matter who paid for the compute around a piece of data that is about me. It matters that it's about me. And because it's about me, right, I should own access to and propagation rights to that data, whether I want to delete it or not. Now, clearly there are some legal ramifications. If I'm a felon, it's in the public's interest for the public to own that data. Yeah, there's rights about that. But in general, do you have the right to consume and use the cookies on my computer to define behavior for others or myself? Do you have the right to give me a different price because you think that I will pay more than the guy next door? You're using my own data about me. And so the privacy constructs, these value systems are important. And these principles, I think they're going to get another 10 years before we get this ironed out. It's important for you guys to think about those value systems and not so much you don't have to solve the world's problems, but you should form an opinion, right? And this is the value system part of what are our principles as we apply these capabilities and skills that we have as we grow up, right? Yeah. I told you why I learned my lesson and how, and it is, I'm not particularly proud of the fact that I built those systems at scales right? I went to work on my first Teradata system in 1988. And in 1990, I was working with my first 100 gigabyte table. And it was behavioral data at a telephone company. And what we did was figure out who to sell larger and more expensive packages to, who would not utilize the resources available to them. And at the time, I didn't understand that was not a nice thing to do, right? So anyway, these systems that you're going to be building, I'm not trying to tell you what the public good is that you should use or how to make a profit or anything like that, just that you should have an opinion. So the data privacy thing to me is very important. And I'll tell you the personal reason why to wrap it all up, right? I have 2 disabled children. And early on in my career, I was a part of a nonprofit and we did a whole lot of advocacy. And it was my 15 seconds of fame. And what I discovered was being a public figure is not very much fun. And so I learned about that need for privacy after it was taken from me. And those systems that I built, right now, you know why I regret them.
Thank you for sharing that story, Michael. I think the purpose, no matter what we do in business, in our career, having that purpose of what is the bigger goal, what is the value we are defining for ourselves and going after, it's so important. That's again, I think it's much larger than solving any specific business problem. It's about life purpose and the value for life. I think those are very important points. Thank you for sharing those.
Yeah.
You know, as we were going through all that you were sharing, we heard about several use cases from you, of course. You talked about, data privacy use cases. You talked about how at Teradata you build systems that would help you sell more at the checkout at the stores, all that. But I wanted to ask you more about, could you share more, industry use cases of how to apply big data? So really applying big data technologies into the industry and discussing some of those use cases. Could you share some of those in addition to what you've already done?
So there are quite a number of big data use cases. I think that one of them that we're going to see more and more use of is statistical bootstrapping. And we don't see it used very often, but essentially what a bootstrap does, well, you guys you've all taken statistics. But in large data sets, let's say that you have a problem where there's 100,000 categories and you have a distribution which leaves 20% of your categories with not enough data to individually predict statistical baseline. And this is a way in which you can use all of the other data to predict in each one of the categories a reasonable set of behavioral baselines. And then you use that baseline forever. I know that the one that we did at eBay in 2008 is still being used to feed the A/B testing system. So when they roll out a new piece of software, they're very precise about which categories they roll out the new functions into, right? And they also use that to test fatigue, right? Because statistically, when you build a new function, or when you're sampling sets in ABC testing and production systems, you have to be careful not to always use the same set as your initializer, right? So I think the big data is going to start getting used in ways that statistically we haven't used them before. There was a principle that I instilled at both of those companies, which I think is just now starting to become effective in the industries, and that is that there's no reason to sample data anymore. I know that we teach those things in college a lot because, frankly, we only have laptops, and the data doesn't fit there. But as we containerize things and use the cloud, that will become less and less the case. Don't sample. How many times have you guys done some sampling and then spent half of the next meeting or whatever arguing about the effect of the sampling? So don't sample it. And in fact, what I used to tell these guys, all my data scientists at those companies is, hey, look, I spent a lot of time building you a system that has a complete set of data. I also built a bunch of things so that you could ask reasonable questions of the complete set of data. So stop sampling it. Use a fact-based decision, because then you don't have to worry about it. The only bias you have to worry about is what data didn't we collect? Okay, that's it. So the larger the data set that you want access to, right, we need to change our thinking still to this day. Stop thinking about the data set as, how do I sample it so that I can go do this complete thing? Move the function to the data, right? You hear those data guys talk about this all the time. Don't move the data to the function, and there are times to do that, don't get me wrong. Move the function to the data. And this is really, really true in the data science process today. And don't subset it. Go work with it. Work with the data. And so I think in these large data systems, we're going to see that as a systems function of how, what's the business process and the methodologies that we use to go look at the data. In more practical terms, the big thing that I've seen of late, which you guys are probably going to grow up with, is a separation of compute and storage. And I alluded to this earlier in talking about the fact that most data used to be a function of the software system that created it and maintained it. That's not the case. And this is exemplified by the separation of compute and storage, in which all the storage and the serialization form that that data resides in, which by the way is an optimization, separate subject, but every time you serialize a piece of data, it's serialized into an index. Therefore, it's an optimization. Serialization is about optimization. But when you separate compute and storage, what you end up with is when you operate on the storage, serialized or not, you're operating on it with independent compute engines. And so whereas we used to build an enterprise data warehouse and your operational interface to that data was through the compute engine, you had to come in the top of the compute engine through SQL to get to it. Today, we moved that layer. So now I can have very specialized compute engines. Think about a relational data store, TensorFlow, right? And a custom application all operating on the same data sets. Yes, there's a locking problem, just put that aside. Conceptually, right, the reason why you have to do this is TensorFlow has its own deserialization forms. It knows that it's going to look at relations on disk, and it has to generate tensors from that, okay? Relational database, never going to understand that, never. And so only in the last 5 years has the technology implementation at a macro level come to the space where we have separation of compute and storage. This is actually why cloud is important. And we'll see the entire industry change into this methodology. But it will be about engines and the form of data on disk. So that's actually the systems use case. There are a bunch of use cases from the business perspective. I think, we talked about ad impressions earlier. I think that's probably going to change. I think we're going to start to see microservices which users build. And we'll start to see dynamic function creation, which get used in very interesting ways, right? We see websites doing this already, in which you define your own ecosystem. And I don't have any examples for you, but this is some of the places where separating data from its generator is really going to change how we view functional things. And I'll leave this one last plug. I was at I was at a conference in Lyon about, maybe it was 10 years ago or so. And the guest speaker was from Carnegie Mellon, and he ran their game architecture lab. And they were talking about how to simplify programming constructs. And so you look at the gaming engines today, which are founded on those architectures that they built. And there are several interoperating engines. One of them looks at what is the landscape, right? So what is the playing field in some things? Another thing looks, and this is, by the way, called actor-based programming, right? So I have several kinds of engines which interact to create the environment and the constraints, and then I set up a set of rules and attributes for an actor. Can he have a gun? What can the gun do, right? What can I toss? How can I interoperate with the other actors? And then they let the engine deal with the billions of states, right, that are available. Now, by the way, most people don't realize about gaming engines is that they're essentially founded on the constructs of time slice theory. Every gaming engine has a clock because it has to go through on that cycle, which is typically 60 clock cycles a second. It has to go calculate all of the states and then display them. And this is why GPUs are very, very important. This should also give you a clue into why virtual reality is so difficult to do. It's not a display problem at all. Yes, there are display problems in virtual reality, but it's not a display problem. It's about managing the number of states, right? And so you see these kinds of things as we roll forward in the architectural constructs of why self-modifying function will be important, right? How does it respond to a set of predictions and modify its behavior without screwing up all of the contracts that it has around itself, which gets into API definition and other things, which we're not going to talk about today. But to your point, how are we going to apply these things? we're going to see a merging of things. The latest and greatest thing that I saw was watch Apple and watch how their individual products are going to place them at a point in which all of a sudden their entire ecosystem will be enabled by virtual reality or augmented reality. Look at this, what do they call it? They call it spatial audio now. They just introduced this stuff. And so when you turn your head, the sounds turn with you when your headphones are on. Okay, that's great. When the glasses come out 2 or 3 years from now, right? How are those two things going to work together? This is what's happening as a byproduct of some of the things where data now drives the functions. Right? They have an end state goal, and they now have the data, right? And so it's about the ecosystem. So watching Apple get into augmented reality is going to be very interesting from a product perspective.
And that's their priority for the next few years.
Oh, I'm not working on that stuff. I have my hands full just dealing with storing and managing data. And, you know, I'm a data guy at heart. I get to watch people like Apple and the government and others deal with these data systems that I help them basically organize and understand. That's the job that I have for the most part. How do you make some of the world's most complex data understandable to people who don't have to manage that, right? Data management is me. And so I'm going to wrap this up with one common thing. I've mentioned this a bunch of times. I swore that I would get to, I didn't swear, I didn't do that. Data is a prime. And, we have thought for a long time, when I was on the mainframe, it started with the hardware, and then you had software that was written around the hardware, and then data was a byproduct. And that entire ecosystem is flipped over. And so the management of data, right, and thinking about data as its own thing is somewhat difficult to do. When do you generalize it? An example is, we tend to think in the relational world in terms of entities and attributes, primary keys and foreign keys and things like that. These are relatively abstract constructs that actually have very, very important principles. I can tell you, for example, that just about every API in existence is based upon the primary key of some data set. We never think about it that way, but it's true. The function is founded on the description of how the data is laid out. And so paying attention to the form of data and its construct and applying appropriate governance to how do you build a contract between two systems. What becomes a public data feed, right? Here's another example of how data is a prime. A data system or a system that generates data, all your OLTP and web systems, right? They're responsible for creating the public data set, not the downstream system. We saw this in the EDW world for years and years. I've got a bug in the data. The data's wrong. And so we'll fix it on the data consumer side. That's the wrong place, right? It's about the data. It's not about the software system, and it's not about the business process, although all those things are intermixed, right? So when you think about data, think about it as a standalone thing, right? And when you do that, that data will now have a lifespan of its own, and many different computing systems can interoperate with it, which means that you have to define it, you have to care and feed for it, you have to write documentation about it. Its provenance becomes incredibly important, and that you can have access to that provenance and how that gets used to build metrics, right? If you guys, there's a whole nother conversation we could have about primary, secondary, tertiary metrics generation over all sorts of different topics, time in particular, and what metrics are important to measure, right? But the foundation of that is your data has to be consistent, and you have to know how it was built. First thing a data scientist is going to do is going to go investigate his data, right? Doesn't matter what functions he applies to it. If he doesn't understand the data, he can't get anything out of it, right? And so if you go look at any of the writings of our friend Nate Silver at 538.com, shameless plug for a guy I don't even know, he is a data scientist. And so you read some of his articles, and he goes through and explains every data element in the building of a model and why it's important and how he trims off the things that are not and combines those things to make a predictive function. It's a great example. Some of the reading is dense, but it is the best example of treating the data as a prime.
There's so many databases, Michael, that are out there that today, because of the big data, we got new SQL databases, open source, as well as the ones coming from large corporations. We got, of course, so many NoSQL databases as well. I'm making a distinction from new SQL. And of course, relational databases that are or have been there. How do you see an enterprise adopting so many of them for different use cases? That complicates the overall data architecture, if you will, because instead of the old days where you just had one database that pretty much did everything for you, and you didn't really have a lot of big data. When I say big data, I mean the variety and the volume and the velocity and all the other V's. But today we got so much source of data coming and so many sources from where the data comes in. How that complicates the whole thing so much that I'm just curious to see what your thoughts about that.
Well, about 5 years ago, I was thinking about the next generation of Aster data. And we built an interesting thing where we bound the Aster data technology to Teradata. But I had to kind of think about the foundations of why was this important, right? What was it about Aster that was actually really important, and what is the foundation of that? And I mentioned earlier that we have to look at the data engines as being just that. They're compute engines. It's not about the storage, it's about the compute engine. Because what a compute engine does is it operates on a particular form of data for this or under the service of a particular kind of functions. I mentioned TensorFlow, but let's also talk about like Neo4j, right? Graph system. It's an MPP graph system. And then there's relational databases. Now, relational databases are incredibly flexible. And you can write, for example, you can do graph work in a relational database. It's hard, but you can do it. We've got GIS modules in relational database, as Postgres has proven. That doesn't mean it's the right place for them. Now, the problem becomes, how do you integrate data, but the form of the data for consumption by multiple types of engines? And I use these three engines in particular because right now they're the largest of them. But you can also think of gaming systems as an engine as well. If you look at tensors, right, which is essentially a vectorized network, right? Then you look at Neo4j, which is a graph, and then you have relations. Well, relations are pretty simple, except that they're really not, right? But what we did do with relations is we described the algebra. Now, the problem is that each one of these systems needs access to largely the same set of data. And so they need some functions so that they can understand how to utilize that data. And this is why I think that the form of data and its descriptive properties is so important. Because if I have a boundary condition in a TensorFlow issue, not related to the functionality, but of the data itself, that boundary condition is going to expand in its complexity and error rate in the other two systems. And so I think that us being really prescriptive about what a piece of data is and its macro properties, its metadata, is going to become increasingly important. And we tend to think of this as governance, and it is, but it's also a little bit higher order than that. Now, let's talk about NoSQL databases and NewSQL and all those kinds of things. The NoSQL databases came up because there are a bunch of great use cases out there in which SQL is kind of a problem, right? It is very difficult to write systems quickly in SQL. It's declarative and it's somewhat obtuse and difficult to deal with on purpose. And its intent was to create parse trees that are optimizable, right? And so the isolation is in the engine. In a NoSQL system, and let's just take Cassandra, because it was really the biggest and first one of those, right? Cassandra is a fabulous write engine. It's simple. You define your own API, and the engine does all the orchestration behind the scenes, ordering all your IO and taking care of that stuff. And what it gave up was locking, right? Because you don't need it when you're doing tuple-based, simplistic kinds of things. What do you need all that locking for? Particularly in a 10,000 node ecosystem. I do not need to lock the whole thing, right? And so this begets eventual consistency. Now, I think the systems guys got a little far away from themselves because it was the systems guys that said, we're going to do away with the relational databases, not knowing a damn thing about data, right? And so they got into trouble. And there are problems with eventual consistency. This entire thing is about, if I follow the paradigm, separate the data, take care of the data on its own because it's a prime, and then apply the right functions and capabilities of data engines to that data. And we now have enough knowledge and enough technology to be able to apply the right engine to the right set of functions. Yes, we got to deal with locking problems, right? And relational systems, say what you want, but the definition of ACID is when you need it, there's no doubt about what you have to do. And we just don't have ACID in NoSQL systems. We don't, by definition. By the way, I worked with a fabulously different implementation of NoSQL at REAC. I was at a little company called Tapjoy, which does incentivized ad-based systems for gaming. And they used a big REAC implementation. And so if you ever want to see about something in which you see the implementation of small transactions in a parallel way, go look at the architecture of REAC. It is a fabulous implementation, but it's founded on the principle that I have a small enough unit of work that the locking really doesn't matter. I do not need to lock an entire object for the insertion of a single tuple. And so when I look at these systems, they're all fabulous. We just need to think about them as apply the right compute engine to the right problem and take care of the data by itself. If you take care of the data and you make that data known and public, and you apply data principles to it, whether they're relational or otherwise, then these systems can build contracts at runtime and be dependable. I hope that answers your question about that. I know that it kind of veered around that, but they're all important systems. I'm a fan of the data, and relational systems is where I grew up, but relational systems aren't perfect. And we just, so as technologists, I think we need to be careful about acknowledging what they're good for and what they're not. This battle over, NoSQL versus SQL is kind of like asking the question, is VI better than Emacs? It is the same set of problems, right? It doesn't matter. Which tool are you going to use for which job is the right question. I hope that covers that ground. I know that a lot of times what I think isn't very popular, but it's more about how do you get to the base set of values and principles and apply a reasoned decision.
I completely agree, Michael. I think that's one of the key principles, that applying the right technology for the right problem. Don't think of it as relational versus NoSQL, because they all have their purpose. And that purpose, their advantages, their disadvantages, where they really excel at. I think those are the places we, as big data architects, have to really apply and understand where's the right tool for what purpose, and apply that in your corporations.
Yeah. There's one important thing that we didn't get to talk about. I know we had intended to talk about this in the pipelines, but we didn't talk about the complexity of how pipelines are, we're essentially today moving the hypothesis proof of concept code directly into production. And so what we end up with in an ecosystem is a matrix of pipelines. And from a macro level, we're creating immense amounts of tech debt because we didn't implement the governance to describe to the developer when to go generalize that pipeline, right? So he creates a point-to-point pipeline, does his own serialization in between, uses some custom transform and transport format, and Kafka doesn't understand it. Kafka, Storm, take your pick of these generalized. Well, so where's the governance and standards which says, look, okay, you proved your hypothesis. Now you need to write this thing in the standards that we have in this environment. And that piece is missing. Now, there's one sideline bar to that, which is that there is a construct in architecture which we rarely talk about, which is the lifespan of systems. And you and I know that everything that you and I touch in a big ecosystem is probably going to last for 15 to 20 years. Average, let's just call it 15 years, right? This is how I know that I'm not going to be maintaining the code that I wrote for that. Ashish, always a pleasure.
Thank you, Michael.